Okay, so what I wanted to talk about inside of this video is I wanted to talk about internal validity to help you with some of the definitions and give you a real sense of what it means to have for an experiment or a study to have internal validity. So the internal validity of an experiment refers to the ability of our experiment to show that a change in the independent variable causes a change in the dependent variable. So what we want to do is we want to be able to ascribe causation. So you want to remember there are three requirements for causation. One, there is a mathematical relationship between the independent and the dependent variable. Two, the change in the independent variable comes before the change in the dependent variable. Three, if there is no change in the independent variable, then there is no change in the dependent variable. Okay? So those are our three requirements. Without the three of them, we have challenges to causation. So like if we have any problems with A, B, or C, that's when we have a problem with internal validity. Okay? So if we look at this, we'll look at them kind of like one by one, and we'll talk about what are those challenges and those things that might cause issues in internal validity. So the first requirement for causation, that mathematical relationship, is generally not an issue for internal validity. It's more of an issue with adequate sample sizing and issues with sampling. Okay? So we find a mathematical relationship after we take data. If we've taken sufficient data or we've done that properly, then what we get is we either going to get a mathematical relationship or we won't. And if you don't have a mathematical relationship, what are you going to do? Go back to the drawing board. Okay? The second two are really about experimental design. And so those are the two that I'm going to concentrate on. So the change coming before the dependent variable and the absence of the independent variable, meaning that there's no change in the dependent variable, those are issues very much related to internal validity. Okay? So let's take a look at the first one. That is the change in the independent variable coming before the change in the dependent variable. All right, so let's talk about this idea of correlation and causation. All right, you may have heard this before in your stats classes. Okay, uh, in causation and correlation, we're asking ourselves the question of which variable comes first. Okay, a correlation means that we actually have a mathematical relationship. The two things actually are happening at the same time, or we see them in tandem with one another. Okay, but what that doesn't tell me is that doesn't actually tell me which one's coming first. All right. So, like for example, an increase in blood serum cholesterol and the development of arterial plaques. All right. So here's the thing. What we have is we have a patient. The patient comes in, right? Okay. The patient has, on the one hand, has high blood cholesterol. They have high cholesterol, and they have large plaques. Okay. So those two are seen together. All right. On the other hand, we might see a person that has low cholesterol and small plaques or no plaques. Okay? And oftentimes what we've been taught, right, and what was very much in vogue for 50 years inside of this country is that high cholesterol leads to large plaques. Okay? And that low cholesterol leads to small plaques, small arterial plaques. But there's a little bit of a problem. How do I know? How do I know that arterial plaques don't cause cholesterol? Cause blood serum cholesterol, excuse me. What makes us believe that high blood serum cholesterol is the thing that leads to large plaques and not that large plaques is the thing that leads to high cholesterol? Or that small plaques, right, okay, means that we're not going to get the increase in cholesterol and so we're going to have low cholesterol. Not that having low cholesterol leads to no plaques. Okay, so this is a question that researchers have to answer because that's the question of whether or not one precedes the other. If I am going to assume, if I'm going to say that high cholesterol or cholesterol is my independent variable, and my dependent variable is the size of the plaque, okay, then I need to show, right, need to show that this is the relationship. Okay, so that's the thing that I need to show. Okay, if I can't do that, then the problem that I have is a problem of internal validity. It's basically saying, you know what? I don't buy it. Yeah, you got a mathematical relationship, but high cholesterol doesn't necessarily lead to large plaques. Large plaques could lead to high cholesterol. And this is what's called a correlation and causation problem. Correlation, the mathematical relationship is there, but we don't have cause. We don't have cholesterol causing plaques yet. We need something else. We need more work that will allow that to happen. Okay? Our next issue with internal validity is whether or not in the absence of the independent variable, we'll get a change in the dependent variable, right? That's basically saying that the only thing that's causing a change in the dependent variable is the independent variable, right? So let's ask this question about saturated fat and coronary heart disease. So this is actually like a really hot button issue that's shown up inside of diet and nutrition. And it's very much a hot button issue because of the issues that have shown up with like the studies that have shown that saturated fat and eating saturated fat causes coronary heart disease. Okay? So basically what they were is they were basically correlation studies, they're epidemiological studies. So what happened is that somebody tracked the amount of saturated fat that Americans were eating and showed that that coincided with an increase in coronary heart disease. Okay, so like for example, we got saturated fat intake, and then over here is percent coronary heart disease. And essentially, that graph looked like that, right? As we increase saturated fat, there was an increase in coronary heart disease, which is fine, right? Like that actually is called a correlation. This is like a correlation. Correlation is there. So we have a mathematical relationship. We see it. It's sitting right there. But at exactly the same time, okay, there was an increase in consumption of refined sugar. And so if we look here, now we've got a graph that looks exactly like, it looks basically the same. The percentage, the consumption of refined sugar increased, and at the same time, the percentage of coronary heart disease increased as well. Well, which one's doing the work, right? Which one of these variables, and this is a big question, which one of these variables is responsible for the increase? Okay? Which one is it? Is it the saturated fat intake or is it the consumption of refined sugar? That's a challenge to internal validity. If I make the claim that saturated fat intake, right, causes coronary heart disease, then I have to show that, you know what, if I took away the saturated fat but kept the consumption of refined sugar, that I would get a drop in coronary heart disease, right? I would not actually get this increase. And it turns out, right, over time we're seeing that this consumption of refined sugar actually ends up being a really, really important indicator or important maybe cause of coronary heart disease, right? Okay. So consequently, that's the idea. The idea here is like which one of these variables is responsible for the increase. If I can't tell, that means low internal validity. So let me write that down. If I can't tell, then low internal validity. Give you another example. Okay, oftentimes researchers there's a lot of there's a lot of pressure to show that their interventions are actually the things that are helping, right? So like say for example you've got an intervention for ADHD, and you're looking at some attention tasks for kids, all right? So what you do is, right, you give the attention task, right, the one that's meant to improve attention, to 45 kids with ADHD, right? And then at the end of 6 months, you notice an improvement in attention. Was the improvement due to the tasks? And that's a really important question, right? Is the improvement actually due to the tasks, right? Well, here's the problem, okay? Attention increases as we age. How do I know that the improvement is not because the kids got older? That's maturation. It's not due to older kids. Well, in my setup, I don't know. That's a problem. It has low internal validity, right? The low internal validity is due to the fact that I cannot eliminate maturation as a reason for improved attention, right? So one of the ways that I might actually deal with that to improve the internal validity is to, in fact, add a control group, right? A control group would improve due to maturation. And then what I would do is I would figure out, hey, well, did my task group actually improve more than the control group? Okay. So in this case, we have low validity because I have a lurking variable. This is the thing that might be doing the work. Okay. Aging might be doing the work. Might be the cause of the change. Okay. When we have difficulties with determining if the independent variable is responsible for the change in the dependent variable, this is the problem with internal validity. Okay. If we have great confidence that the independent variable is the one doing the changing in the dependent variable, then that's high validity. But if we have low levels of confidence in the ability of the independent variable to change the dependent variable, like that's what we've shown, then our experiment has what's called low internal validity. Okay? And that's our definition. All right? So, if I were trying to figure out whether or not my experiment actually has high or low internal validity, what I would do is I would go through and I would think through the experiment, right? We've got, on the one hand, we'd ask ourselves, is it correlation and causation issue? Can I not ascribe one to being first and the other one to being second? All right. In some cases, it's very natural. We know that it is the case that um, you know that one comes first and second. Say, for example, in pre-test and post-test interventions, right? First and second, that's something it's built into the experiment. On the other hand, in some cases, like our issue with cholesterol and plaques, we might have a little bit more of an issue. Okay. Secondly, we want to ask ourselves, if there is no change in the independent variable, am I still going to get change in the dependent variable? And that's a question of confounding and lurking variables. Do I have a lot of confounding and lurking variables that actually may be the things that are responsible for my changes inside of my dependent variable? Okay. And if I could sit there and I kind of poke holes in the experiment and go, you know what? What about this? How did you deal with that? Right? Okay. How did you deal with that? Then what I end up having is I end up having low validity, right? That's the instance where a researcher comes in and he goes, how do I know that your results actually are the results that you're claiming, right? Your validity is low, so I don't believe it. I don't buy it. All right. This completes the video.